combining functions and composite functions. We can do some different operations with functions. First of all, we can take the sum of two functions. We add them by adding their rules. So f plus g of x would be the f of x function plus the g of x function. We can take the difference of functions. F minus g of x is going to be f of x minus g of x function. So subtracting their rules. Be careful to watch the order because subtraction is not commutative. Product of two functions, f times g of x is going to be f of x times g of x. And the quotient would be f over g of x is f of x over g of x, dividing the two rules. Again, watch the order. And in this case, g of x cannot equal 0 because we cannot divide by 0. Now the domain of the sum, difference, and product of f and g consists of all real numbers of the input variable for which f and g are defined. The domain of the quotient function consists of all real numbers for which f and g are defined, as before, and the added restriction that g cannot equal 0. Example 1 is operations with functions. If f of x is x cubed and g of x is x minus 1, find the following functions and give their domains. So f plus g of x, by definition above, is f of x plus g of x. That is going to be f of x being x cubed plus g of x being x minus 1. Our job after this is to simplify. There are no like terms to put together, so we're finished with this one. F minus g of x, by definition, is the f of x function minus the g of x function. So we have x cubed, and we're subtracting the g function, x minus 1. Now it is a binomial, so we're putting that in parentheses so that we are sure to subtract the entire function, not just the first term. So we do need to simplify by distributing that negative through the parentheses, and we're finished. F times g of x is the f of x function times the g of x function. So this is going to be x cubed times all of the g function, x minus 1. When I multiply, I'm going to have x to the fourth minus x cubed. Now the domain of these three functions, as stated above, is going to be the domain of f and also the domain of g. The domain of f is all real numbers. You can take any value of x and cube it. Nothing bad is going to happen. You can take any value of x and subtract 1 and nothing bad is going to happen. So the domain of g is all real numbers. So the domain of f plus g, f minus g, and f times g is negative infinity to positive infinity. Separately, we'll do f over g of x. That is f of x being divided by g of x. This is x cubed divided by x minus 1. There's nothing more we can do to simplify this, so that's it. We do need to find the domain. The domain of f over g is the same as the domain of f plus g, f minus g, f times g, and the added restriction that the g of x function cannot equal 0. The g of x function cannot equal 0 means that x minus 1 cannot equal 0. So x cannot equal 1. In other words, we can choose any real number on the real number line and be okay as long as we're not picking the number 1. So the domain of f over g is negative infinity to 1 union 1 to positive infinity. Example 2 involves revenue, cost, and profit. The demand for a certain electronic component is given by P of x equals 1,000 minus 2x. Producing and selling x units of this component involve a monthly fixed cost of $1,999, and the cost of producing each component is $4. Write the equations that model total revenue and total cost as functions of the units produced for this electronic component in a month. So we'll call these the R of x function and the C of x functions. The revenue is going to be the demand times the number of items produced. So 1,000 minus 2x times the number of units produced. C of x is going to be 1,999 plus $4 times every component produced. Write the equation that models the profit as a function of the units produced for this component during a month. Well, your profit is going to be the revenue brought in minus the cost. So we're simply taking the R of x function, which simplified is 1,000x minus 2x squared, minus all of the C of x function. So make sure to put that in parentheses. When we simplify that, we have 1,000x minus 2x squared minus 1,999 minus 4x. Now we have some like terms we can put together. So we'll have negative 2x squared plus 996x minus 1,999. Now we want to find the maximum possible monthly profit. Think about how this is attainable. Look at the profit function. Our profit function, P of x, is negative 2x squared plus 996x minus 1,999. This is a quadratic function. It results in a parabola. It is a downward opening parabola. So when we are finding the maximum possible monthly profit, we recognize that the word maximum is the key word to tell us we're looking for something about the vertex. One way we can do this is to put this into the calculator. And graph it. Let's set our window to go from 0 to maybe 500, and we'll do a zoom fit, and we do see the vertex in that window. So we can second trace to go to the calculate menu and find the maximum. Left bound, we hit enter. The right bound, move over to the right of the vertex and hit enter, and then hit enter one more time, and your maximum is at 249, 122,000 3. So when we're asking for the possible monthly profit, X is the number of units. This is going to be the profit. So the maximum possible monthly profit is $122,003. Make sure to put that $sign on that as your label. Example 3, unconventional vehicle sales. In December 2010, the U.S. Energy Information Administration, the EIA, presented results projecting rapid growth in sales of unconventional vehicles through the year 2035. The figure shows the number of light-duty cars and trucks in each category sold in millions, projected to the year 2035. The functions that model the number of each type of vehicle sold in millions are listed below, where X is the number of years after 2000. Part A, let's add functions F and D to obtain a function that gives the total number of flex fuel and diesel vehicles sold. F plus D of X is going to be the f of x function plus the d of x function. So I'll have negative 0.0027x squared. I have these two x values. I can add 0.193 plus 0.028. That gives me a plus 0.221x, and my 0.439 plus 0.077 gives me plus 0.516 after I add my constants. Add functions h, m, and e to obtain a function that gives the total number of hybrid and electric vehicles sold. H plus m plus e of x. Adding our squared terms, I have negative 0.006 plus a negative 0.001. That gives me a negative 0.007x squared. Adding my x coefficients, 0.025 plus 0.35 plus 0.081. I have plus 0.456x, and adding my constant terms, I have 0.154 minus 3.380 minus 1.115. That gives me a negative 4.341 as my constant. Let's graph the functions from part A and B on the same axes for the years 2000 to 2035. Clear out your previous function. We'll enter our two functions that we've obtained. Double check to make sure you don't have any typos. And we're going to graph these from the years 2000 to 2035. So let's set our window from 0 to 35. since X is the number of years after 2000, and do a zoom fit. And this is what our graph looks like. In part D, graph the functions from parts A and B on the same axes through the year 2050. So let's change our window to be from 0 to 50 and do another zoom fit. Will the number of hybrid and electric vehicles exceed the number of flex fuel and diesel vehicles before 2050, according to the models? If you go back to our functions, we have these functions. This one is in blue, is this, and this one that's in red is the function from part B. So they want to know, will the number of hybrid and electric vehicles exceed the number of flex fuel and diesel vehicles? Will the red be higher than the blue before 2050? And we see the red is always lower than the blue. So we'll have to say no. Now, based on this graph, do the models appear to be good predictors of unconventional vehicle sales after the year 2035? After 2035, let's do a trace here. Get onto the hybrid electric vehicles over there and type in 35. After 35, it appears that our graph falls. So there's no reason after the year 2035 that the number of those sales would decrease. It should only increase. So again, this is not a good model after the year 2035. In part E, we're adding the functions from A and B to obtain a function that gives the total number of unconventional vehicles sold. So we'll add up our x squared coefficients. That gives me a negative 0.0097x squared. Move this over so we have a little more room to write. And we'll just call this t of x, the total of all of those unconventional vehicles. I'm going to add my 0.221 plus my 0.456, and I get plus 0.677 x, and I'm adding my constants now, 0.6, and that's going to be a negative 3.825. So that is my function that gives the total number of unconventional vehicles sold. According to the EIA projection, there's going to be 8.1 million unconventional vehicles sold in 2035. Does this model agree with that 8.1 million prediction? Well, let's see. In 2035, x is going to be 35. So we'll say a negative 0.0097 times 35 squared, putting that in for x, plus 0.677 times 35 minus 3.825. And we get about 7.9875. So T of 35 is about 7.9875. Does the model agree with this prediction? It's very close. It's very close in agreement. So 8.1 million unconventional, 7.9875 as far as trying to predict something in the future, and there are lots of things you can't determine that will happen. It is a very close prediction with the model as well. Average cost. A company's average cost per unit when X units are produced is the quotient of the function C of X, which is the total production cost, and the identity function, the number of units produced. So the average cost function is C bar of X equals C of X over X. Example 4, average cost. Sunny's greenhouse produces roses, and their total cost for the production of X 100 roses is C of X equals 50X plus 5,000. Let's form the average cost function. Average cost, C bar of X, is going to be the total cost divided by the number of units. For which input values is C bar of X defined? And give a real-world explanation of this answer. C bar of X is defined for all X that are not equal to 0. As long as X is not 0, this function is defined. In the real world, however, we would also not allow negative numbers because X is the number of units produced. So X, the number of units produced, cannot be negative. That's because we cannot produce a negative number of units. Graph C bar of X for 0 to 5,000 roses, which is 50 units. What can you say about the average cost? Let's go ahead and place those functions in y equals. So we have parentheses 50x plus 500. We want to make sure that we put the entire numerator in parentheses and divide by x. You can do it like that, or you can also use alpha y equals and use your fraction template. So it would be 50x plus 500 and x in the denominator. They want us to graph it from 0 to 50. We already have those in there. And let's do a zoom fit. So you can see, we can even trace this as our x value, as the number of units, that's what x represents, as the number of units increases, then y is representing your average cost per unit. Your average cost per unit decreases. So as the number of units produced increases, the average cost per unit decreases. Composition of functions. The composite function f of g is defined by f composed of g of x, which is f of g of x. So f is composed of or made of g of x. G of x is the ingredient that is being put inside the f function. The domain of f composed of g is the subset of the domain of g for which f composed of g is defined. The composite function g composed of f is defined by g composed of f of x equals g of f of x. So if g is written first and it's composed of f of x is the ingredient that is put inside the g function. The domain of g composed of f is the subset of the domain of f for which g composed of f is defined. Example 5, function composition in orange juice. There are two machines in a room. One of the machines squeezes oranges to make orange juice, and the other is a canning machine that puts the orange juice into cans. Thinking of these two processes as functions, we named the squeezing function g and the canning function f. So let's describe the composite function f composed of g of orange, which by definition is f of g of orange. Just like any part of algebra, when we have nested parentheses, we work on the inner set of parentheses first and simplify. We move to the next set of parentheses and simplify, and then the last set of parentheses. So our first set of parentheses, the first things to do would be to take g of orange. So what this means is f of, what does g of orange do? G is squeezing whatever you put into it. So f of squeezing orange. Now, squeezing orange is put into the f function. So after we've squeezed the orange, we can the squeezed orange. Or we've canned juice. Describe the composite function g composed of f of orange, which is g of f of orange. So here, again, we work on the inside. F of orange would be canning an orange. So we're going to can oranges. And then after that, we move to the outside function, which is squeezing it. So we're going to squeeze the can of oranges. So which function, f of g of orange or g of f of orange, neither or both, makes sense in the context of this problem? This one is the one that makes sense. Example 6, finding composite function outputs. Find the following composite function outputs using f of x equals 2x minus 5, g of x equals 6 minus x squared, and h of x equals 1 over x. Give the domain for each new function formed. Part A, h composed of f of x, which is by definition h of f of x. So this is h of f of x, h of, instead of writing f of x, we actually put what f of x is. F of x is 2x minus 5. h of 2x minus 5 now is, well, the h function takes 1 and divides by whatever the input is. If this was h of 3, we'd have 1 over 3. If it was h of 17, we'd have 1 over 17. We're saying h of 2x minus 5, so it's 1 over 2x minus 5. Give the domain of the function that's formed. Well, we know that we have to look at the function that comes out and decide, are there things that we cannot allow x to be? Of course. We have x in a denominator, and we want to make sure that that entire denominator does not equal 0, because we can't divide by 0. What would cause that entire denominator to equal 0? Well, we can solve this inequality, and that shows us that x cannot equal 5 halves. We also have to determine what the domain of the input function was, which is 2x minus 5. The domain of that is all real numbers. So this is the only thing restricting our domain. Our domain then is going to be from negative infinity to 5 halves, union 5 halves to positive infinity. F composed of g of x, which by definition is f of g of x. We first work on the inside function. G of x is 6 minus x squared. Now we take that 6 minus x squared and put it inside the f function. What does the f function do? It takes 2 times some input and then subtracts 5. 2 times some input and then subtracts 5. That input is the 6 minus x squared. Now we need to simplify. 12 minus 2x squared minus 5. So that's a negative 2x squared plus 7. Looking at this function, it does not have any restrictions. We can take any real number, square it, multiply it by negative 2, and add 7. Nothing bad is going to happen. We don't get anything that's undefined or non-real. When we look at the input function, 6 minus x squared, the same thing, all real numbers. So the domain for this function is negative infinity to positive infinity, because we have no restrictions on that output function, and we have no restrictions on the function that was the input. G composed of f of x, which is by definition g of f of x. So this is g of my f of x function is 2x minus 5. Now we're going to take 2x minus 5 and put it into the g function. The g function says 6 minus whatever the input is squared. The input is that 2x minus 5. So this is going to be 6 minus 4x squared minus 20x plus 25. Then I'm going to go ahead and distribute the negative through that set of parentheses, and then combine like terms. I'll go ahead and place it into descending order. There we go. Now there is nothing about this function that comes out that says there's a restriction on x. The function that was put in, the 2x minus 5, has no restrictions. So the domain is going to be all real numbers, no restrictions on the input. Example 7, combinations with functions. If f of x equals the square root of x minus 5 and g of x equals 2x squared minus 4, we first want to graph f plus g of x using this window and then determine what the domain is. So we can actually go straight into putting this into the calculator. the f of x function, square root of x minus 5. Make sure that you arrow right to get out from underneath that square root. And we're adding 2x squared minus 4. Let's set our window to the dimensions that they've asked, -1 to 10 on the x and 0 to 200 on the y. Graph, and this is the graph that we have. So what is the domain? The domain is going to be the combination of the domains of these. So we have no restrictions on this, but we cannot let anything into this function that would cause a problem. It's okay to use 5 because we can have 5 minus 5 is 0 and the square root of 0 is simply 0. But if we put anything less than 5, we'll have negative numbers under the square root, which would give us a non-real result. You can even look at the table. Let's say that I start my table at 0 and I look through my table. The first integer we see that it is defined for is 5. So the domain is going to be from 5 to positive infinity. Now let's graph f over g of x using this window. So we'll say the alpha y equals, you can use that template, square root of x minus 5, and the denominator is 2x squared minus 4. Window from 5 to 15 on the x and 0 to 0.016. Let's graph. Looks very interesting there. And what is the domain of f over g? With this one, we need to go back to our definition with the domain of f over g. It'll be the domain of f and then excluding anything that would make the g of x function 0. So our domain of f is simply 5 to positive infinity, including the 5. With g of x not equaling 0, we'd have 2x squared minus 4 cannot equal 0. So 2x squared cannot equal 4, which means x squared cannot equal 2. So x cannot equal plus or minus the square root of 2. Let's see what the square root of 2 is. So we're saying that the domain of g is anything but negative square root of 2 or positive square root of 2, but it can be anything before, between, or after those two values. Since we have to satisfy the domain of f being greater than 5, this is really of no consequence. So we know that our domain of f over g is going to be the same as the domain of f. Now we want to compute f composed of g of -3 and g composed of f of 9. F composed of g of -3 is f of g of -3. So we'll do the inside first. G of -3 is going to be 2 times -3 squared minus 4. So that is f of 9 times my 2 and then minus 4. So this is 18 minus 4, which is 14. I've simplified the inside as much as I can, so now I'm going to take f of 14. The f function takes the square root of whatever your input is minus 5. So this is the square root of 9, which is 3. G composed of f of 9 is g of f of 9. So this is g of f of 9 is going to be the square root of 9 minus 5. So that is g of the square root of 4, which is g of 2. Now g of 2, we're going to say 2 times 2 squared minus 4. 2 squared is 4 times 2 is 8 minus 4 is 4. That does it for this section, so go ahead and dive into the homework and let me know if you have any questions.